Hello and welcome to another new paper summary. Let us wind the clocks a year back and talk about ResNets. Yes, that's right, ResNets in 2023. Deep Residual Learning for Image Recognition is a foundational paper in the deep learning community that introduced Residual Networks or ResNets. Normally, as you add more layers to a deep learning model, it should get better at its task because it can learn more complex features. But in practice, deeper networks often don't perform as well as expected. They can be harder to train due to vanishing and exploding gradient problems. To address this, the authors introduced a simple yet groundbreaking idea. Instead of trying to learn an underlying function directly, why not just learn the difference or residual between the current layer's output and the desired output? This is done using shortcut connections or skip connections that bypass one or more layers. Imagine you're trying to solve a math problem. Instead of calculating the answers from scratch, you use a previous problem's answer and just figure out the difference between the old problem and the new one. The difference is the residual. ResNets use these residual connections to effectively skip layers, making it possible to train very deep networks, like 152 layers deep, without the training process getting stuck. When tested, these ResNet architectures set new performance standards in image recognition tasks. So let's try to understand the problem. The paper aims to ask a central question. In terms of deep neural networks, is deeper always better? Think of training a deep neural network like trying to pass a whispered message in a game of telephone across a long line of friends. To make it more interesting, the first person whispers a puzzle and a group of progressively smarter friends tries to decode it. But the catch, of course, is the more friends or layers you add to the line, the harder it gets to keep the original message intact by the end. A game of telephone is still not considered a formal framework, so we must once again resort to maths. Capital F is the class of all functions together with weights and parameters, which means that for all functions small f in capital F, there exists a set of parameters that can be obtained through training. F star is the optimal function that we want to approximate by finding the minimal possible loss from the data x labels y, and for a function small f, provided that it belongs to the class of bigger functions f. Now it can be hypothesized that a more powerful class of functions, and let us call this f bar, will be better at approximating f star. So with training, we aim to find more and more powerful f bar that will eventually approximate f star. However, with f bar not including the original f, there is a possibility of f bar not approximating f star at all. So the solution is to nest the function classes as we go forward. In other words, this means the progressive function classes must contain the original function class in some respect. This means making sure some of the friends in the string of friends occasionally hear the original puzzle. In the context of the paper, they are suggesting that when training a deep neural network, instead of trying to learn a complex function directly, it's sometimes easier to learn the difference or residual between the input and the desired output. This is achieved using shortcut connections that skip certain layers. These connections help make the learning process easier without adding extra complexity. Let us examine how the authors propose the solution. Firstly, they propose the solution to be something called deep residual learning. What is residual learning in the first place? The original learning problem, as shown in the left, is to train a neural network to approximate a function h of x. However, this can be difficult for deep neural networks. Deep residual learning reformulates the problem by letting the neural network approximate a residual function f of x, which is hx minus x. This is equivalent to approximating hx, but it can be easier to learn. The degradation problem is the phenomenon where the training error of a deep neural network increases as the network becomes deeper. This is because it becomes more difficult for the network to learn identity mappings, which are ideal mappings for the first few layers of the deep neural network. Deep residual learning can help to solve the degradation problem. The next part of the solution is identity mapping by shortcuts. The authors present the residual learning building block, which consists of two parts. First, the residual function fx of fwi, which is a stack of layers that learns residuals between the input x and the desired output. The shortcut connection, which adds the input x to the output of the residual function. The shortcut connection is important because it allows the residual learning building block to learn identity mappings. An identity mapping is simply a function that returns its input. Identity mappings are ideal mappings for the first few layers of the deep neural network because they do not change the input data. Finally, let's take a look at the architecture. The plane network is inspired by the philosophy of VGG nets. It has a convolutional layers mostly with 3x3 filters and follows simple design rules. The residual network is based on the plane network. It inserts short connections which turn the network into its counterpart residual version. The code for the residual block is actually pretty straightforward, which it should be given the simplicity of the residual block itself. But ResNets came in 2015. Why is it still so relevant? In deep neural networks, the vanishing gradient problem can occur because you multiply many small numbers together, like when you calculate gradients during backpropagation. The results become even smaller, leading to gradients that are too tiny to help the network learn effectively. This happens especially in the deeper layers of the network. Skip connections, also known as residual connections, help address this problem. By allowing information to skip layers and directly connect with deeper layers, you're essentially bypassing the multiplication steps that cause the gradients to vanish. When you use skip connections, the activations in the deeper layers get some extra input from shallower layers, which prevents them from becoming exponentially small. This is crucial, especially when using saturating activation functions like tanh, which can make the vanishing gradient problem worse. Like all great architecture, ResNet has evolved as well. ResNext is a natural extension of the original ResNet architecture. It introduces the concept of cardinality, the number of parallel pathways or branches within the residual block. DenseNet, short for densely connected convolutional networks, have each layer receiving input from all preceding layers. This results in a highly interconnected network. Wide ResNets is a variant of ResNet where the width of the network or the number of channels are increased while the depth is decreased. The adoption of residual connections has gone past just CNNs. Many modern architectures and domains now use the concept of direct connections between layers. The most notable is transformers, a popular architecture for natural language processing tasks and beyond. It incorporates residual connections in their design. Each sublayer in a transformer, such as a self-attention or feed-forward network, has a residual connection. And it has been vital in the training of transformer models. Augmix is a data augmentation technique that blends multiple augmentation policies. While it is not a network architecture, it has some residual-based designs in itself. Also, deep learning models like AR models, such as some variants of transformers in NLP, can benefit from residual connections for stability in deeper architectures. But if ResNets are so great, why not sprinkle them everywhere? Every architecture is new, and thus every problem has to be separately examined. But we must remember a few things. Nested function classes have a higher probability of containing the optimal function only and only if the network is deep enough. Residual learning is beneficial when learning the residual gives the network a higher advantage than optimizing parameters efficiently. Adding too many shortcuts will force the network to learn X much better than the features it might discover. This results in overfitting.